C, or more precisely, if f with j, this becomes an integral. J vector also has the integral g. If you're working in 3 dimensions to a 3 dimensions vector, there is to the impulse. A force times, more precisely, integral with respect to it's important to us. Actually, it's not quantity, power, energy, but it is some kind of impulse momentum. Which is now to the work energy terms as a total work by all of the forces is equal to the change in the object's kinetic, the impulse here, the impulse acting on that. In other words, the sum of the impulses that are acting to the change in its momentum. I wanted to run an example of the impulse little something with power. Suppose that I have an object, and let's say it's an object of mass 3 kilograms. Here it is, and I'm going to be pulling on it with a force. X. Object. And now I'll tell you what that force is. Another time, seconds, of course. And here we are. 1, 2, 3 Newton. 1, 2, 3, 4 seconds. And here is the graph of the force. It's 1 Newton the first second, and then 2 Newton the next second, and back to 1 Newton, and 0. So I grab onto this for 1 second, 1 Newton, and then 4 seconds, and I pull it gently, and I'll get going. After those 4 seconds are up. So that's the graph for the first, for the second force applied to a mass 3 kilograms, constant force, constant acceleration. I apply to the find out in 1 second. Then the force up to 2 newtons, it doubles, and calculate how it will be going after 2 that new force. And same thing there, tack them all together and find out this procedure for the perfect impulse here. The impulse acting on this integral of the area curve. I can calculate the area point to here. Very but that actually you turn off something large. After you would see my fist or something, and of course. So how are we doing? Force suddenly change. More realistic problem if you want, but spoil the example was that we fixed. Unit. Second. I started from is 3 kilograms times v adding through v or 3 or per kilogram. That's a weird unit. Per kilogram, what is it? That the mass kilogram meter per second kilogram meters per second. So it's meters per second. It should be newtons per second. But this, if you happen to know the 4 time the medium change it. Common sort of problem. Now, main subject for center of mass. Let me set the scene by imagining that we have a stick, so maybe a meter stick or so, on which I've glued a bunch of weights. So let's call this the x direction. 1, 2, 3, 4, 5. I don't care what those are, centimeters or meters. Well, it can be meters if you can get it all on a meter stick, I guess, but whatever unit of length you care to use here. So I'm going to stick some masses on there. I've glued on here a mass of 6 kilograms. Okay. Here a mass of 1. Here a mass of 4. Nothing here, and a mass of 3 over here. So that's just going to be my working example. Suppose masses are strung out along the x-axis. The center of mass, by center of mass, I mean the average of those positions. The weighted average, actually, what the word sounds like, center of mass. If you have 2 equal masses, for example, M and M, where would the center of mass be? Well, that would be right halfway in between, right? But suppose that this one was 2M and this one was M. Then the average of the 2 positions, in one sense, is still the center, but the weighted average, where I weight them according to the mass, in proportion to the mass, the weighted average, the center of mass, would shift over here in favor of the heavier one. In fact, it would be 2/3 of the way across. Make sense? If this was 3m, then the center of mass would be 3/4 of the way across. In other words, I always weight each one in doing the averaging process, weight each one according to its mass, in proportion to its mass. Make sense? It's exactly the way that you would set up the notion of center of mass to give you first confronted by the problem. How do I write this? Weighted in proportion to its mass. So this one, the 6 kilogram, is going to count a lot in this. The 1 kilogram is not going to count away. How would I write down that formula? X, I use a capital X here for the center of mass, is equal to 1 over the total mass times the sum of each mass, mi, times its position, xi, from I equals 1 up to n, however many masses you've got. That's the formal definition of center of mass. The sum, each position weighted by the mass, multiplied by the mass at that point, and then divide by the total mass to get the average. M equals total mass. Somehow or other, the formal definition is hard for me to get my teeth into, or hard to think about. I want to run some examples now so you see how it goes. See what I mean by weighted average? By the way, if I asked you what's the average of the ages of all the people in this room, how would you do it? We would go along and interrogate each person, and what's their age, age of I, the age of the ith person. We would add it up over all the people here, and then we would divide by the total number of people in the room. Isn't that right? That's how you would calculate it. But if you wanted to weight those averages, so heavy people count more, you might multiply each one by the mass of that person, and then divide not by the total number of people, but by the total mass of everybody in the room. Then you would have a weighted average age with people that are having more. I don't know why you would ever be interested in such an average, but we are interested for reasons that will appear in due course. So, example 1. Find the center of mass of those objects. So, for that particular set, what would the center of mass be? X equals, first of all, the total mass. What's the total mass of the whole works? These were the masses. These are the positions. So the masses are 6, 4 is 10, 1's 11, 12, 13, 14. I see a total of 14 there. So 1 over 14. And now I want to sum up the individual masses, each one multiplied by its location. So it would be 6 times 0. This is supposed to be y-axis here. So that's at 0. Plus 1 times plus 4 times 2 plus, last one, you tell me. 3 times 4. 3 times 4. See how it goes? Very easy. 14 of 0 plus 1 plus 8 plus 12 is 21 over 14. How nice. 7 goes into those. 3 over 2. 1.5. So let's put that in here. Where is 1.5 on this diagram? Right there. That's where the center of mass of that. Make sense? Yeah, this one is way over to the right, but it's only 3. Over here I've got 6. What does it represent? There are many different ways that center of mass actually comes into physics, but one way of saying it is, suppose that I glued all of these masses in appropriate places onto a stick, and then I attach a string to the stick. This is the place where if I attach the string there, it would just perfectly balance. If I attach this string here, it would be too heavy and it would flop down. If I attach it over here, this side would be too heavy, it would flop the other way. But the center of mass is that position where if you suspend the thing from there, it's let me show you a, I was going to say a trick, I don't know whether this is or not, but a convenient fact about calculating center of masses, and that is that you can collect them in subparts if you want to. For example, I'm going to find first the center of mass of the 6 and the 4 alone, and then I'm going to find the center of mass of the 1 and the 3 alone, and then I'm going to treat the whole thing as though I just had 2 masses at those 2 locations and get the center of mass of the whole thing. That was a mouthful. Did you understand what I? Well, let me do it. How shall I say this? You can count them. You can treat the whole system in pieces if you like. Sometimes, as in an example I'm going to show you in a moment, this is a very quick way to calculate centers of mass. That I don't know how to say this in words that will be any more sensible than that. But here's how it goes. Watch the idea. I take first the 6 and the 4, or you can do any pair or 3 of them if you want. I don't care. But let's do the 6 and 4. First of all, the total mass then is equal to 6 and 4 is 10, and the center of mass of just the 6 and the 4. So this is the 6 and the 4 alone. The center of mass would be 1 over 10 times the 6 is at 0, and the 4 is at 2. So this is 4 2s are 8 over 10. I'll just leave it like that. So the 6 and the 4 by themselves are the equivalent of a single mass, 10, at the point 8/10. Now let's do the same for the 1 and the 3 alone. One and 3 alone, what's the total mass in that case?
1, right?
1 and 3.
1. You mean
4.
Oh, you mean masses 1 and 3.
Just the sum of, yeah, the masses of those. The total mass is 4, 1 plus 3, and the position of the center of mass of those 2, the 1 and the 3, would be 1/4 then, 1 over the total mass, times, let's see, 1 at position 1 plus 3 at position 4 is equal to 1 plus 3/4 or 12 is 13 over 4. So the 1 and the 3 alone are just the same as as far as calculating center of mass is concerned, are just the same as if we had put a mass of 4, a single mass that combines the two, of 4 at the point 13/4. 13/4 is a little bit more than 3. So let me redraw the scheme here then. I've got 1, 2, 3, 4, along in the x direction. And what I've just argued is that this system is exactly, the system of all four is exactly the same as far as calculating center of mass is concerned as putting mass 10 at the point 8/10, which is 4/5, so it's about here. So I would put 10 at that location. And the 1 and 3 alone are like a mass 4 at the point 13/4. 4 goes into 13/3, so it's 3 1/4. 1, 2, 3 1/4, right about here. And it would be 4 kilograms there at 13/4. So I say the original configuration is, as far as center of mass is concerned, exactly equivalent to those two pieces. Now I calculate the center of mass of those two pieces. What do I get? X equals the total mass, 10 plus 4 is 14. Where have I seen that before? Times the mass here, that's 10, times its location, 8/10. Plus the mass over here, that's 4, times its location, 13/4. Notice the cancellations here, and I get 8 and 13, which is 21. So 21/14, which is 3/2 once again. So the center of mass of the whole thing is 1.5, just as I got before. Do you see the point? I'm sorry for all the arithmetic, but the point is this, that you have a lot of leeway in calculating the center of mass of a combination of systems. If you like, you can do it for the whole works all at once. If you see an easy way to do it by combining some portions together, and then do it that way, by all means, and reduce it down to a simpler problem. Let me show you an example of the latter technique in a situation where it gets the center of mass stupidly easily. And you get another example of it on the OWL, I think, for Friday. So here's an example. I take meter sticks, a couple of meter sticks, and stick them together. Or any old rods. All I want is that I've got several identical uniform rods. So here's case A. I'm going to take two of them and join them together like this. So they're identical rods here. Each one has mass m, and they got the same length also. Got the picture? I'd like to know, where's the center of mass of that system? Well, you tell me first, where is the center of mass of this stick alone? A uniform meter stick, is that obvious? Right in the center, isn't that right? So at the 50 centimeter spot, that's the center of mass of that one. The center of mass of this one, likewise, right at the center of it. So this is equivalent, as far as center of mass is concerned, to one mass m located here and one equal mass m located over there. So what's the center of mass of the whole system then? Well, I can draw the line joining one to the other, and it's exactly halfway along that line, isn't that right? So, center of mass is right there, and I didn't need to do any calculation at all. I don't know whether these examples are too stupidly simple or whether you're completely mystified by what I'm doing. I hope it's the former. So all I'm trying to show you is how you could use this fact that you could chop the system into subpieces if you want to get very quick center of mass in certain circumstances, not always to be sure. But here's another example with meter sticks. Let's take 3 of them now. And there's one. And now I'm going to join the second one like that. And then put a third one equal length. here's M, M, and M, and I'd like to know what's the center of mass of that system. Well, that's perfectly equivalent to a single mass point here, and a mass point here, and a mass point down here. Now suppose that I combine these two, ignoring this one for the moment. What would the center of mass of that combination be? Well, obviously halfway along this line. So that would be the equivalent of putting 2m, because there were two of them, at that center point there. So the whole thing is equivalent in the first instance to 3 m's like that, but these two are the equivalent of 2 m's in the very center. So now I just have to do a combine 2 m's there and 1 m there. I draw the line between them, and the center of mass is going to be 2/3 of the way up. So it would be somewhere about around here. Well, this raises the whole issue of center of mass in two-dimensional or three-dimensional cases. This is a particularly easy one where I was able to chop it up in such a way that it always became a one-dimensional problem. But what if it's fundamentally three dimensions? Then instead of thinking about where on the line on a stick I would attach my string so that the whole thing balances, I imagine that I've got a whole plate, massless plate, thin sheet or something, that I glue the objects down on, and then I say, where on that plate can I dangle the whole plate with the masses on it in such a way that it will be at equilibrium and won't tip over in any direction. So what is the center of mass in 2 or 3 dimensions in that way? Well, it's exactly the same as 1 dimension, only I need to do it separately for each dimension. So the x component of the center of mass, if you like, is 1 over the total mass times the sum of mi xi. But meanwhile, y, the y component of the center of mass, is 1 over m times the sum of mi yi. And similarly, the z component of the center of mass, 1 over m sum of mi zi. Some people like to combine that whole thing into a single formula that says r, the position of the center of mass, is 1 over the mass, the vector position of the center of mass, times sum of mi times ri, where ri is a vector position of each one separately. This formula is, definition, is maybe useful theoretically, but in practice, when you're calculating these things, the first thing you do is go to the individual components. So let's do an example. Example of a two-dimensional array. So here it is. I picked some numbers that will work out reasonably well. Here's x and here's y. And now I want 1, 2, and 1, 2, 3, and actually I'm going to go down to -1 on the y-axis. So -1, 1, 2, 0, and then this is 1, 2, 3, and so on. And now, where am I going to stick the masses? I have, at this point here, I'm going to stick 5 kilograms. At this point down here, the point x equals 2, but y equals -1, I'm going to stick 3 kilograms. And over here at 3 and 1, I'll stick 4 kilograms. And we want to find out what is the position of the center of mass of that arrangement there. Ready to go? Well, x, that's equal to 1 over the total mass. Total mass in this instance is 12, huh? 5, 4 is 9, 10, 11, 12. So 1/12 of. Now, do pay close attention to how I do the sum over here. It's each individual mass times the x component of that mass's position. So, for number 1, I've got 5 is the mass. And what is the x component of its position?
1.
1. The reason I say watch closely is that some people say, no, but wait a minute, it's up 2 units in the y direction. Don't I have to somehow or other take the hypotenuse or something like that? No, it's much simpler than that. Just the x component of its position, that's the only thing that matters. And now 3, and its x position is 2. 4, and its x position is 3. Total, 1/12 of 5 plus 6 plus 12. 12 and 6 is 18, and 5 is 23. So 23 over 12. That's the x position of the center of mass. Let's see what that means on this diagram here. 23 over 12, 24 over 12 would be 2, so that's a hair less than 2. That means that the center of mass lies on that line there. I don't know yet how far up or down it is. That's going to come from the y component. But the x component is 23/12. So far so good? Okay, how about y? This is 1 over 12 times 5. You tell me.
2.
2, good, plus 3, you tell me, minus 1, watch out for that, minus 1, take the signs literally, plus 4 times 1. So it's 1/12 of 10 minus 3 plus 4. Did I do that right? 10 minus 3 plus 4, so it's 10 plus 1 is 11. It's 11 over 12. That's the y component of the center of mass. Where's my love? Oh, here we are. 11/12, that's a little bit less than 1, huh? So would be right along that line. Evidently, the center of mass is right there. Seem about right? Yeah, somewhere kind of in the middle. If you had got, for example, an answer that the center of mass was out here, you would know you'd done something wrong. Right? It's got to be somewhere within the triangle constructed from those 3 lumps, obviously, and it should be, you know, with preference for the 5 because it's a little bit heavier, a little bit closer to the 5 than it would be to the other 2, but somewhere inside that triangle, surely. Got the picture? Okay, next step. Suppose that the mass was not in discrete lumps like this, but was continuously distributed. Actually, I did a couple of examples here, but the first thing we did was replace the continuous distribution by a point at the very center. So what if you couldn't do that? What happens to the theory for continuously distributed mass instead of just mass point? Well, you can imagine what's going to happen. Instead of the sum here, I'm going to have an integral. X becomes 1 over the total mass times the integral. I'm going to chop the thing up into not just n, but now an infinite number of pieces, each one of which has a mass, let's call it dm, and I multiply that by the x, where it's located, and integrate it up. So it becomes the integral of x dm. Do I need to write down the similar thing for y and z? I don't think so, obviously. Same story, only I put in a y and a z. Now, actually, when mathematicians look at that, I think that's weird. How on earth do you calculate an integral with respect to dm? That doesn't seem like a variable that I don't know how to get my teeth into. This is true, but this is nice notation. Nice notation, and in the context, it immediately will suggest itself what you should put in for dm to convert that over into something that you can actually integrate in the usual way. So let me do some examples of continuous distributions. Be thinking about how you would do the problem if you were faced with it, as I describe it. Suppose that I have a uniform bar. Let's say a meter stick. We should have had one. What's the center of mass of the meter stick? Right at the middle, of course. In fact, I only used that one, but let's prove it, if you will. So here's the bar. I do this one just because we know the answer, and it's so simple that it doesn't raise any mathematical complications. Here's the bar. And it goes out to length L, let's say. And I would like to know, what is the center of mass of that thing? What I'm going to do is chop it up into pieces, a little piece here, that little hunk, which is out at a distance x and has a width, let's call it dx. Now you tell me, what is the mass of that little chunk, what we'll call dm? If it has a width dx, I never told you what the mass of this whole thing is. Its mass is m and its length is L. So what would you write down for dm, the mass of that little chunk that's length is dx? Let's see, it would be the mass per unit length of this rod, isn't that right? Times the little length, which is dx. So I say its mass per unit length, that's m over L, times the length of that little segment, dx. Now you see I have switched over from dm, which mathematicians gag at, to dx, which they're perfectly comfortable with. But what was the translation scheme? It was mass per unit length. Okay, let me plug it into the formula now. This says that x should be equal to 1 over the total mass, capital M, times the integral of x times dm, which is m over capital L, times dx. And what limit should I integrate that between? 0 at the left-hand end? Capital L at the right-hand end, huh? M over L, I see that's a constant. Might as well haul it out in front. So this is 1 over m times m over L times the integral from 0 to L of x dx. Now I've got this into the form of an integral that's absolutely unambiguous. The m's, by the way, cancel out, and I get 1 over L integral of x dx. X squared over 2. So this is x squared over 2. Differentiate that, you get 1/2 2x. So that's right. Evaluated at the limit 0 and L. If I put in the upper limit, I get L squared over 2. The lower limit, I get 0. So this is 1L cancels, lo and behold, L over 2. How about that? Is that what you expected? Good, me too. Not a very deep problem, but it's just to illustrate the technique. Let's do a little bit more interesting one where I think the answer is by no means obvious. Suppose that I have a triangular plate. In fact, we'll make it a right triangle. And I want to know what's the center of mass of that triangular plate. So what are we up to now? Example 5. I'll stick it in the with one vertex at the origin. And let's see, let's give it some dimensions. I'll say that the x dimension is A and the y dimension is B. And I want to know where is the center of mass of that thing. You tell me, first of all, in the x direction, where do you expect it would be? Sometimes a handy thing to think where you imagine the answer, what the answer should be before you start calculating anything. Just as far as the x direction is concerned, halfway across? No, more or less than that.
More.
A little bit more because there's more stuff out here, right? So I think that it's going to be somewhere over there. Certainly not over here, certainly not halfway across or over there. Somewhere between halfway across and all the way across would be, I think, pretty clearly where it's going to come out. But now let's work it out. So x, first of all, the x component is equal to 1 over the total mass of this thing times the integral of x dm. Now, how am I going to chop this into pieces? I want to chop it into chunks that are all the same distance x from the origin. So I draw a sliver like that. All of those share the same value of x, and I'm going to give them a width, as before, dx. And now I would like to know, what is the mass of that piece? Well, I say it's the mass per unit. I didn't say this, but this thing is supposed to be uniform, a uniform triangle. So you took a piece of nice uniform plywood and I cut a triangle out of it. And so it's not as though there's a big old hunk of mass up there and much lighter down here. Something that's uniform mass density over the whole thing. So what is the mass of that sliver there? I say it's the mass per unit area where area A is the area of the triangle. We can figure that out at our leisure. Mass per unit area times the area of that sliver. What is the area of that piece? Well, the width is dx. And what is the height? You know, let's just call that y for the moment. Is that okay? Y is the height of that thing, and of course, as I go along, y is going to be increasing and decreasing. So, but this switches me over from m over to x, which I can get my teeth into. I have 1 over m times the integral of x times dm, which is the mass per unit area, times the area y dx. And I'm going to integrate that over what limits? This is an integral over x. So it runs from 0 up to a. M and A are constants. Why don't I pull them out in front? In fact, I'll cancel the M while I'm at it and write this as 1 over the area times the integral from 0 to A of x, y, dx. Y I cannot take outside the integral because it's changing as I go along. Now I'm stuck. I've got two different variables in there. I'm trying to do an integral with respect to x, but I've got a y in there. What is y as a function of x? If x is this distance here, and y is that height there, can you spot the formula? The formula for this line, actually, y is equal to the slope. That would be rise of b over run of a times x. Isn't that right? Yeah. Y over x is b over a by similar triangles, if you want to think of it that way. That's the formula for that line there. Y is equal to b over a times x. Let me plug that in here, and now I really can do the integral. 1 over a integral 0 to a of x times b over a, which are constants, times another x dx. I'll haul a b over a out in front, so it becomes b over a times capital A, integral 0 to a of x squared dx. Integral of x squared, x cubed over 3. So this is b over a times x cubed over 3, evaluated at the limit 0 and a, lower limit nothing, upper limit a, so it would be a cubed b over 3a. Whoa! It's a mess. But I never put in what a is. What is a in terms of the dimensions of this triangle? It's a half the base times the altitude, right? The base is a, and the altitude is b, so it's just a half ab. So that tells me that x is equal to a cubed b over 3a times capital A, which was 1/2 ab. Now let's see what we get out of this. A and a squared cancels 2 of those. The b cancels completely. I bring the 2 up into the numerator, and I get 2/3 a. Make sense? Yeah, that's kind of where we thought it would be. A little bit more than halfway across. In point of fact, it's 2/3 of the way across. Ask you a quickie. Where is the center of mass in the y direction? So we now know that in the x direction it lies along there. It's 2/3 of the way across. In other words, at 2a over 3. That's x. Can anybody tell me what y would be without doing any calculation at all? Halfway. Halfway up, you say? No, I don't think so, because there's more stuff down here than there is up there. 2/3 of the way up? No, that would be even worse. 1/3 of the way up. Evidently, the rule is it's always 2/3 of the way across to the fatter side. So 2/3 of the way from here to the longer side would be 1/3 of the way up. So y is equal to b over 3 actually for the triangle. We'll do some more complicated examples next time. I'll show you what this is.